Once again, we're back to the dark, and you should be able to see the electron beam created within the E over M apparatus. And I've temporarily turned off the current through those Helmholtz coils, but I'm going to go ahead and turn it back up again, and we should observe what happens to the electron beam in the presence of that large uniform magnetic field that's created by the Helmholtz coils. So the beam is deflecting downward, and I'm not going to see all of the observations that I want if it deflects downward. So I'm going to take that back down and simply change the leads on my Helmholtz coil so that I send current in the other direction through the coil. And now, when we create that magnetic field, you'll notice there's clear deflection of the electron beam, but it's not just being deflected in between those. In fact, it's not being deflected at all between those charged plates before. This is a magnetic effect, and it's being deflected everywhere in that region. So let's just get that approximate shape. And you'll notice there that the beam makes a circular trajectory in the E over M apparatus. And that's due to the fact that there's a force being applied on that electron beam from the magnetic field created by the Helmholtz coils, and that force always stays at a right angle to both the direction that the beam is moving and the direction that the magnetic field is pointed. The direction of the magnetic field stays constant in this setup from one coil back to the other coil, but as the beam moves, that force changes its velocity, and then it has a new velocity direction. The force is now perpendicular to that direction, and the overall result is circular motion, which hopefully you recall from your work in Physics 1. This is an electromagnetic example of centripetal forces, forces that cause objects to move in circular trajectories. The next question says to, within appropriate limits, vary the amount of current that's going through those coils, which varies the magnetic field strength. Well, right now we have about 1.6 amps going through, and so let's watch and see what happens to the circle when we increase the current, which increases the magnetic field strength. If I go the other direction and decrease the current, the next question asks us to vary the potential difference that's applied to the charged plates, and that, you'll recall, is responsible for how fast those charges are moving in the system. So right now I have a potential difference of about 100 volts, just under 100 volts, 99 volts. If I increase that voltage to make the particles move faster, there's what happens to the circular trajectory. If I decrease that potential to make the particles move slower, that's what happens to the trajectory. The final question says, feel free to perform other experiments of interest. Obviously, you're not here controlling the apparatus, and there's nothing else that's essential for the observation that we want to make here, but there are a couple of interesting things to note. Number one, if you turn that bulb slightly so that the velocity is initially not directly perpendicular, then you actually get a little spiral path here. Or you have one magnetic field from the coils, and you can add in other magnetic fields from external magnets, and And I'll play our very crude video game of steer the electron beam around. But the main piece that we want to get out of this observation is that when I have moving charges in a magnetic field, they experience a force, and that force is perpendicular both to the direction that the charges are moving and to the direction of the magnetic field.